Okay, good afternoon, everyone. As you can see, I am not Sabela, but I will host the CNM talks today. I hope that you don't mishear and enjoy today's presentations. Usually, in these talks, the speaker presents their research line to do something new, using different technologies or technological procedures, increasing the state of the art of their scientific fields. But today, Jofre Pallarès will introduce us a different starting point. To perform his research, he needs to deconstruct something to understand how it works, usually piece by piece or layer by layer. Using this information, he could propose new strategies to analyze its functionality and the functionality of the different elements that compose it, looking for a way to interact with them. This way is known as reverse engineering and helps us to reconstruct the functionality of an object from the analysis of its component parts. For us, the reverse engineering process is not concerned with creating a copy of the original products. It is only an analysis to understand their technological features with little or without any additional knowledge about the procedure involved in their original fabrication. In the integrated circuit field, we could use reverse engineering techniques to analyze the logic blocks integrated on an IC, ensuring that all of them do and only do the expected performances without any undocumented functionality, in order to guarantee the security and the integrity of the logic and communication systems. In the next talk, Jofre Pallarès will present the EXFILES project. This project aims to provide law enforcement agencies with new tools to extract data from mobile phones in a strict legal context. Well, Jofre, the floor is yours.
Okay, thank you, Salva, for this nice introduction. Well, we have 15 minutes. Fortunately, it's not so much, and I will not be able to present many technical things, nice images. Sorry, I will be centered more in the project and the problems. So here we have the outline. I will make an introduction about why we need this project. Then I will present the project, and finally I will explain our role inside the project and a little nice example to get you some picture of what we are doing. Okay, so let's start. This project it's about digital forensics. Okay, and when people think about digital forensics, most of them think of a bunch of good-looking people working in a big lab with big screens, always working at night with very, very low illumination. Okay, I have to say that, of course, that's not true. Okay, we work during day with nice illumination on our labs, but more or less the job is the same, but with very different things. Okay, let's make a more formal definition of digital forensics. Digital forensics is the branch of forensic science dedicated to the extraction and analysis of evidence found in digital devices. Okay, so it's a clear explanation. We have many branches inside digital forensics, as, for example, network forensics, computer forensics, data analysis, and, of course, mobile forensics, which is a very important one. The digital forensics work is increasing a lot due to that we have many more connected devices every day. Okay? The network usage is increasing a lot. The devices that use this network and store evidences have an increased complexity every year. Okay, and many more devices stores evidences in its memories. So, as an example of the problem we have is that some research magazine called Forensic Focus made a question to the people working in this field in 2015, saying, in your opinion, what is the biggest challenge digital forensic investigators currently face? Okay, so for most of them, the most important problem was the encryption. Okay, encryption, data encryption. Okay, along with other problems, but I can highlight some of them, like lack of training, for example. It's difficult to become an expert in this profession. Okay, there are no publications, for example. Another problem is the growth in digital crime. Okay, as I said. Okay, so let's talk about encryption. Okay? Encryption is one of the biggest challenges in the forensic area. Okay? It's especially critical in mobile forensics because most of the smartphones that you can buy nowadays in the market, they have encryption of the user data out of the box. That means that all the information stored inside the mobile phone, all your personal information is encrypted. Okay. This is a real problem for the investigators when they found a mobile phone and want to get some evidence from the mobile phone, and led to some disputes like the famous San Bernardino killing in 2015. And you can see here when the FBI found a mobile phone from the criminals, and they were unable to extract the data. Well, they were able to extract the encrypted data, but not the plain text. Okay, and they asked Apple to provide a backdoor or unlock the phone for them, and they generated an ethical debate that is still ongoing. This debate, because it's a problem between the privacy of the user and the security. Okay, and opening backdoors on a phone, well, will allow the law enforcement agencies to have a better, improve their investigations, but also will allow some criminals to use the backdoors, or some governments to control their citizens. So it's a real problem, a clear debate. And there, in this point, the European countries are mainly opposed to the idea of letting backdoors accessible. Okay. Why is it so difficult to read data from an encrypted phone? Well, let's see the easy part. A phone that has data not non-encrypted. Okay. So, for example, we have a phone with this kind of data. We can open the phone, check for the memory, the memory chips. Okay, the memory chips usually are fabricated by very few vendors, like Toshiba, Samsung, High-Tech, Hinsec. Sorry. So there are not so much different memories in the market. So just opening this memory chip using a laser, okay, we can expose its wires, and then soldering the wires, the wires that, well, some known wires, then we can extract information. Okay, it's quite easy work. It's only 2 hours, and we use a 150K machine, which well, is not so much. Okay, this photo is not from a mobile phone. It's just for explaining the opening from using a laser. Okay, so it's a safe operation. It's done many times by the LEAs. On the other side, when we have an encrypted phone, okay, the LEAs do not know how to operate, and they have 2 options. One is to use third-party services or tools. Okay, there are cybersecurity firms that provide this service, the open phones, get the unencrypted data, or they provide some tools. Okay, they are quite expensive, of course, and the tools or the service are limited to some family of phones or processors. Another option is to use a side channel attack. Okay, let me explain what this is. Side channel attack is, well, taking the phone, opening, preparing the chip, get access to the chip, and the system on chip, the principal chip of the phone, and then measure some meaningful signal of this chip. When I'm saying meaningful signal, it can be, for example, the power consumption, or it can be the electromagnetic radiation, also thermal, make a thermal imaging, for example, and then compute some critical operation at the same time. Okay, like for example, sending some password or some wrong key, for example. Doing this many million times, we can extract data and using a complex statistical process, well, we can infer the key. Well, when I say we don't do this at the CNM. Also, the laser, we don't do this, but well, this is what the LEAs do. Okay, the problem is that it's a very complicated process. Has critical sample preparation, and you have to make a different setup for every chip. Okay, so well, we have a problem here. Okay, and this is the aim of the project to solve this problem on encrypted phones. This started on 2018, mainly led by the French, the Gendarmerie, and the CSIC research lab. Okay, they started to make contacts to form a consortium, and well, we started a consortium with 12 partners from six different countries, including 5 LEAs. We submitted a proposal on 2018. The name was different. It was called KEM2, Key Enabling Methodologies for Mobile Phones, and we applied it on the security call on the topic Technologies to Enhance the Fight Against Crime and Terrorism, in the subtopic 2, Digital Forensics in the Context of Criminal Investigations. The proposal was rejected with only a 9.5 score, okay, a very low one, but well, since not so much of the, only 4 of the partners were research centers, the other partners thought that it was a good score. Almost everyone involved decided to resubmit again the proposal next year. So in 2019, we resubmitted the proposal with the name EXFILES, extracting forensic information for law enforcement agencies from encrypted smartphones. And we applied for the same topic, but with the subtopic open, that we were advised that maybe we had more possibilities, because if you don't collide with a similar project if you collide with a similar project in a subtopic, then it limits your success. Well, the proposal was with more or less the same partners, only 3 changes, and we made minor changes on the proposal, maybe some things on the aesthetical and the presentation, and we improved the ethics incidents of our proposal. The proposal was approved on 2020 with a 14.5 score. So that's a great score. Okay, and we had a funding of 7 million. And it will be for 3 years, starting on middle 2020. Put the 0.5 in question mark, because maybe due to the pandemic, it will be extended. Okay, I want to remark that well, we had a very different score from the 2 different calls, and the proposal was more or less the same. So I want to well, just to say that if you have a bad score on proposal, do not hesitate to present next year. Okay, because it depends sometimes of the competition. It depends on the reviewers. So well, it's not only depends of the quality of your proposal. Okay, so let's introduce you the partners. This is the consortium. We have 14 partners from 7 countries. 5 of them are LEAs. Only 4 public research institutions. Okay. We have 4 cybersecurity firms and 1 management company. Okay, from Spain we have the CNI as the LEA, Cyber Intelligence, which is a cybersecurity firm, and ourselves. Okay. Well, here I'm presenting the objectives as are written on the proposal. Okay, maybe we can highlight that the objectives of this project is, well, categorize smartphones used by criminals and try to advance the tools, the methods to make reverse engineering on these mobiles, also in a way that can be affordable, okay, and practical. Also, one remarkable objective is try to improve the communication between the different agencies, the different partners, the different stakeholders from different domains, okay, and provide guidelines and recommendations for lawmakers and LEAs, and of course, finally, evaluate the results against real user case. We have many challenges on this project. Maybe the most important ones is the technology, okay, because the state of the art is evolving every day. Okay, for example, from the proposal until the end of the project, we will see 2 different technological nodes in the market. So we have a high risk to obtain obsolete methodologies. Another problem is the management, because unfortunately, the leaders, the people who are driving the project, just quit before starting the project. They get promotions. So it's difficult to lead a project which is not your project. Okay, and also there's the COVID theme. Okay, due to COVID, we don't have face-to-face meetings. We started with a very sad kickoff meeting online. Everyone at their meeting rooms with masks. We could not see the faces of the people we were working. Nobody participates. It's just one direction communication. So it's difficult. Also, we have the legal and ethics problem here, which I think that will be clearly addressed inside the project. And also the problem with the confidential information, because some of the information that we use is classified. And for example, the IMB-CNM, the CSIC partner, does not have access to the classified information. So that sometimes can be a real problem. And also the problem of acquiring chips. So for software tasks, it's not a problem to have many samples. With 2 or 3 mobiles, you can make the work. But in our case, we are used to break many chips. I mean, more dozens of chips before getting the solution. So for high-end mobiles, getting the chips on the market, it's very difficult, and getting the chips from actual mobiles, it's very expensive. Okay, so let's see what we are doing inside this project. Okay, well, the reverse engineering team in the CNM has a state-of-the-art IC reverse engineering capabilities. We are proud of this, but we cannot be lazy because the technology scaling is always one step forward. So, and which is our key point, I think. Our key point, or what differentiates us from the rest, is that although we have a fire reverse engineering lab equipment, we have access to high-end processing and inspection machines. And which is more important, we work with really experts on these machines. I mean, this is a big difference from other partners, because other groups, some guy has to operate the FIB, the bonding machine, the wire bonding machine, sorry, the reactive ion etcher, and also the polishing machine. So, of course, he cannot be an expert on this machine. And our role, well, is very limited to the hardware. Okay, so a part of management and dissemination, we only participate in one work package, the work package 4, hardware approach to extract essential information for decryption. So those are our tasks. Basically, we provide expertise on the layering and reverse engineering the chips, extracting the circuitry, especially the analog one, because we are experts on that. And well, we'll help other partners extracting some information that can be valuable for the interactions with the phones. We have 54 person months, mainly from the reverse engineering team, and the grant for us is up to 400 key euros, and it's led by Dr. Salvador Hidalgo, who presented this session. Okay, so just for finishing, because I'm quite out of time, let me show an example. Some of the images of this example are not the real work, because, well, of course, that's confidential things. Okay, so, well, in this example, I will show how we will read the fuses of a system on chip. The system on chip is the main chip of your phone. Okay, and inside the chip, there is a part of well, there's a matrix of fuses, or several matrices of fuses. These fuses store information that is written just after fabrication by the chip vendor, or maybe after releasing just before releasing the phone by the phone vendor. And usually this information is related to the unique ID of the phone, or the key, or some keys stored. Okay, for example, keys that Apple have to unlock that phone, for example. So let's see how we can read these fuses. We will explain the easy part with this using a dead chip. When I'm saying dead chip, is a chip that will work no longer after our processing. So, well, we start with the chip. This is a common chip, and you have soldered it inside your mobile phone. It's quite huge, 1.5 centimeters each side. It's very thin. And well, what you do is start to remove all the encapsulation and get only the silicon die, okay, by chemical means, or but after decapsulation all the chip starts tends to blend, because it's quite thin. It has a big area, maybe more than 2 square centimeters, but the thickness is below 90 microns, so it bends easily. So what we have to do is use the press, the hot press on the prototyping laboratory, and to planarize the chip over a glass support. Okay, and this is what we get. This is the chip alone, planarized, and as you can see, it's not so much different from the original package. It's quite huge. Okay, after having the chip preparated, what we have to do is remove all the silicon from the bulk. Okay, we will arrive to these fuses from the back side of the chip, or the front side, because these chips have many metal layers, 9, 10. So it's easier to reach the fuses from the backside. Okay, but we have to remove the silicon. What we do is again using mechanical means or polishing machine, and also chemical means. We remove all the silicon, and then we can start to see the chip from the back side. So, for example, this is a matrix of fuses seen from the back side of the chip. There's still a lot of silicon oxide between the fuses and the plane we have, but we can see a lot of silicon oxide in these technologies means maybe 100 nanometers. Okay, so they are not so. Okay, so we have to apply a etching step to remove all this silicon oxide, and then our chip is ready for the imaging. Okay, to do that, we use the e-beam, the SEM from the e-beam, because it has a very nice stage. It's programmable. We can do this thing. We can program this thing the afternoon and let the machine work at night. Okay, and we start acquiring images. And for example, well, we can acquire in one night thousands of images like this one. Okay, this is some detail of the fuse matrix. Okay, and those things here are fuses. Okay, here are fuses, well, clusters of 4 fuses. Well, we have all the images. We have to perform well, some computation to extract exactly the area of the fuse. So, well, it's quite a straightforward thing. And once we have detected all the fuses, we have to crop it and get the images of the fuses. So this is a fuse. Okay, it's not so much, not so different than the fuses, the old fuses that most of the domestic machines had. Okay, this is a thin wire. Okay, of in this case copper, separated into plates, and this is a non-parameter fuse, and this is a fuse. Okay, with a hole that has blown up after the programmation. Okay, so this is quite easy task, I have to say. Okay, the difficult one is one that we are investigating right now, which is making the same with a live chip. When I'm saying live, it's a chip that after discovering its fuses, it can still work. Okay, so it's a very delicate process. It needs many different things, like the other process, like partial decapsulation. Okay, using specialized processing tools. In this case, for example, we have this machine, the EXFILES, that arrived just last month, paid by the project, of course. And this micro milling machine allows you, for example, to reach, to open the encapsulation of a huge chip, remove some parts, remove all the silicon with high precision. Okay, and the chip can be still on the board. Okay. Also, what we want to do with a live chip is can be very challenging because it implies other additional steps like photolithography. Okay, and well, it's not straightforward. So well, that's all. The example. It's time for questions, and I have well, post here a picture of one. Well, I can see the single fuse that we cannot read because sometimes the things do not work as you want, and some particle of dust just well, hit all is hidden here the programmation, and that's all. Any questions?
Okay, thank you very much for this nice presentation. And yes, I'm for questions, comments, suggestions. Any questions from the attendance?
Alexandra Moreno said, why forensic extraction in smartphones and computers are different? Many things. First, the computer has most of its parts differentiated in different chips. Okay, so it's easier to reach the different parts because are physically separated. In the mobile phone, you have a system on chip, and it can include many things. Maybe it can include a processor with graphical processor, with the memory also in the same package. So accessing to these parts is very difficult, and also the encryption. Okay, as I said, by default, most of your mobile phones has all the data encrypted, and by default, most of the computers does not have the data encrypted. So those are more or less the bigger differences. I hope I responded to your question.
Okay, thank you. Any additional question?
You can ask also in Catalan or Spanish. You are afraid to speak in English. There's no problem, eh?
Luis Fonseca, go ahead, please. No?
Jofre,
Sí.
thanks for the talk. You said that the problem you are facing is that you need a lot of chips, and this is expensive. Have you managed to solve this?
Not quite. In some chips, yes. In some other chips, not. It was a real mistake from us, or from many people of the consortium, not to reserve a lot of cash for this. Okay, and yeah. So as I can say, some of the chips and some of the chips is solved, and the others, it's a real problem. We have to go to eBay and things like that, and search for dead phones.
And then you do the job, and you end up with a particle on top of the fuse, no? After breaking up a last generation Apple phone.
You have to take into account that this image, I think, the fuses are less than the fuse cluster is less than 5 by 5 microns. So
it's really
quite
small.
small.
Well, when tourists come back to Barcelona, you can go to the black market. How long does it take, all the things you have explained?
Well, of course, it depends on how you program all these steps with people from the clean room and so on. But I mean, if we were in a hurry and we have made all the, with a good agenda, I think that it can be done in maybe in 3 days. 3 days. Please, Roger, interrupt me if I'm guessing not properly.
You have a question on the chat also.
Yes.
Okay. Xavi Jordà is asking which is the most difficult and challenging device you have analyzed. Well, I cannot respond to this question with precision. It depends. I mean, you can. There are chips that are very difficult to process. Okay, very difficult because due to the technological node. Okay, I can say that we have not worked below 20 nanometers. Okay. But one thing is this. The other thing is the amount of work. I mean, if we have to make reverse engineering of a big chip, maybe the technology is not so. It's not the limiting thing. It's the amount of data you have to process. I mean, the amount of images, the amount of errors you have to correct. Errors like the dust you have seen there. So, well, it depends. It's difficult to answer.
Okay, another question. I have a question.
No, it's the camera that is not.
Which is the more critical step in the project? The step more critical. I assume that the success of the project depends of the provider of the chips or the preparer of the samples or analysis of the results. In your opinion, which is the more critical step in order to guarantee the success of your work?
Maybe not the critical step, but what the most critical challenge is that maybe we can face a phone that we are not capable of break it. For example, a a phone that is very well engineered from software point of view. I mean, it has no software backdoors or unintended backdoors, for example. And on the hardware part, it has well covered many things. I mean, all the critical parts are very well hidden. And for example, the fuses, which store critical information, you have seen here fuses based on metal. There are very different kinds of fuses, but we know that there are some silicon foundries that are starting to make fuses using just transistors, right? But very small transistors. I mean, they are making fuses with transistors, 16 nanometer transistors, so on. So making the job you have seen on these kind of transistors is almost impossible. So maybe this is one of the biggest risks. Of course, we have planned the project to have I mean. The success of the project cannot be measured if we break these phones, but if we obtain new methodologies for other phones, but for me, I think this is one of the biggest problems.
Okay, thank you very much.
Luis,
go ahead, please.
Good morning. Thank you, Jofre, for your presentation. Just one question, because I was not at the beginning of your presentation. I was attending another telco. And I don't know which, the photograph the pictures you showed, to which technology node are you addressing in this case?
Yeah, as I said, I cannot really explain the details. But
just one number: 65, 22, 74.
Below 65, but over the FinFET technology.
Okay, just concerning the availability of chips, let me say that in probably early next year or by the end of this year, we will be able to provide you some few chips on 22 nanometers technology.
Okay.
And for this specific case, probably even you will be able to know at the same time not only the silicon version but also the layout version of some of the libraries. And I understand this could be quite helpful for you.
Yeah, of course, Luis. Of course, for the people who don't know, the ECAS group, who is always designing fabricating a lot of chips, designing and fabricating, is one of our providers of chips. Of course, they do not provide us with mobile phone chips, but sometimes they provide us with chips with the same technology. Of course, as you know, there are not so much companies producing chips. TSMC, Samsung, Global Foundries, and not so much more. And we try to train with the chips from the ECAS group. Okay, train our processes to get information of which are the layers. So we train ourselves first with the chips from them, and then of course with the actual mobile phone chips, maybe we have more experience before starting to break them.
Okay, thank you.
Thank you.
Any additional question or comment, please?
Will quantum technologies change digital forensics in the future?
Yes, very good question, Luis. Yeah. It's what I was saying. The technology is always ahead, so that will be a very big challenge for us. I think that we will have to work as a service for the CNM, but not as a reverse engineering service. No, but just kidding. But I don't know if we will see it. And also, I don't know if the market will adopt these solutions for all the chips. I mean, let's see the chips for automobiles, sensors, and so on. They are still fabricating 0.35 microns, because the technology is enough. The price is not a problem in that case. So, for example, it will be always a market for these big technologies.
Thank you, Jofre.
Thank you very much for the questions. We in this moment, what time is it? We have 40 minutes from the beginning of the presentation. Okay. Any additional comment, question? No? Okay. Well, after 41 minutes from the start of the presentation, thank you very much for your presentation, Jofre, and thank you very much for all the attendance. And I hope you and I hope all of you I wait for all of you in the next CNM talks. Thank you very much, and have a nice weekend. Bye.
Thank you very much.